Okay, in this video, I'm going to do a quick review of domain, and then we'll do a few problems that are a little more challenging. So if you remember back that any input that will lead us to an undefined situation for our range, then we can't use that we have to throw that number out. So we want to make sure we know how to write that in the proper notation. So for this one, x cubed minus 1, any number could go in for x and we'd be fine. So the answer would be any real number. We could also write it as negative infinity to positive infinity. That works. For b, we have b of x equals 3x over quantity 2x plus 1. So for fractions, we don't want the denominator to be equal to 0. So we have to find when that would be the case, and then we're going to restrict our domain to not include that. So I usually just write it like this: 2x plus 1 should not equal 0, and I solve out for the x value, and I get x should not be negative a half. Now sometimes you might see later when we're doing rational graphing, you might say, well, where's the vertical asymptote? And that would be the same thing, and we don't want to use the not equal sign. We would actually leave it as an equal sign to show where the asymptote lies. So just clarify this, but that's what x cannot be. So when I'm graphing, that my asymptote would actually be a dashed line right through there. We'll go over that toward the end of the course. So the way I could write that is in set notation. I would write x as an element of real numbers, although you can kind of skip that part. It's a little more formal, such that x is not equal to negative a half. And then end your braces. You could write it in interval notation by writing negative infinity up to negative a half, but not including union. And then you could write another parenthesis, negative a half up to positive infinity. So those are the two formats we usually use. For part C, it's c of x equals square root of x plus 3. So this radical has a positive index, so we can't have a negative number in there. We can actually have 0 in there. That's totally fine. But we want to set this one up as taking the radicand inside x plus 3, and we do want it to be greater than or equal to 0, and then solve that out. So when we do that, we simply get x is greater than or equal to negative 3. And that's really it. We can just write it in the set notation more formally. A lot of times I just have you write it as an inequality just like that. The other way we could also write it is in interval notation. I'm just trying to see where to fit that. I can put that over here. So I would have negative 3 and then anything, and it's equal to, because remember it can be equal to 0, so I can put a bracket and all the way up to infinity, well, and beyond, I guess. We never stop, so that's why we're never going to bound the infinity. We have our curved bracket. So for part D, this is the same principle now as in B, that we don't want to have 0 in a denominator, but we cannot figure that out without factoring first. So we need to know what our zeros are for that denominator there. So we're going to go ahead and factor first and then solve out for when x would be 0, and that's what we don't want x to be. So go ahead and try that one. Go ahead and factor. It's a good review for you. So you can pause the video there. Okay, so I'm going to put x plus, whoops, need my pen that doesn't disappear, x plus 2 times x plus 1, and that would tell me I can just kind of do this in my head. This one's solving out all x such that x is not equal to -2 and x not equal to -1. Make sure that's an and. We can't have either one of those situations. So to write that in interval notation, I'll jot that down here. You can go ahead and try and make sure you know how to do that. I'm going to pause the video for a second, write that out. Okay, so this is how I would write that. I would have a -infinity to -2. I'm using all curved parentheses, union -2 to -1, union -1 to infinity. So I think the set notation in that case is much easier to use. For part E, we want to find out if e of x equals 1 over x plus 2, if it's the same as function d up here for the x plus 1 over x squared plus 3 of x plus 2. Because what happens here, if I were to simplify d, my simplified version, I would end up getting 1 over x plus 2, which looks like this, right? But the problem is they're not really equivalent because the domains will be different. Because if we look at the domain of E, we would have x plus 2 can't equal 0, so x is not equal to -2, which is part of D but not fully. So in order for functions to be equivalent, they have to have the same domain. So the answer for this would be no, they are not equivalent functions since their domains differ. Okay, so I just wrote that out for you. Sometimes I just pause the video to do my writing so that the videos don't take so long. So now the next part is F. And I think you might be able to try this one on your own because we did one similar. So let's do this one as a classwork, a virtual classwork, or try it on your own. I think you could probably do G also. H and J are tricky, so I'll do those with you. Okay, so the answer for F is going to be F minus X should be greater than 0. So that's a little bit tricky because we have to have the radical to be greater than 0, but we need the entire denominator needs to be, well, the radical is greater than or equal to 0 under a radical, but for a denominator, it has to be not equal to 0. So we need to combine those situations here. So we're just going to write it straight off the bat as greater than 0, and we would get, we can just actually add the x to the other side like this. So we would have 5 greater than x, and then just switch it around, x less than 5. So that is our domain. So it's x is an element of real numbers such that x is less than 5. Again, you could write that in the interval notation to -infinity up to 5, but don't include 5 because we don't want to have a 0 in the denominator. So that one's a little bit different case. We want to look at if G is the same function. So it looks like is F the same function as G? Okay, so looking at this G function, we want to compare it to F above, and they do have the same domain, but that's not the only thing we need to consider. So for this one, we actually wouldn't say it's equivalent because the F function up here does not simplify to be the same exact thing as the g of x. So even though they have the same domain, we're not looking at an equivalency. So it is no. The answer is no. For h, we have, this one's a bit tricky, x squared plus 7x plus 12. So we need to factor what's in the middle there to help us out. We need this whole polynomial under here to be greater than or equal to 0, right? So we're going to factor that would be x plus 3 times x plus 4. And we look at when those are greater than or equal to 0. So it's a little bit tricky to tell unless you actually just graph it. So do a quick sketch. Helps. So we're going to do a really quick sketch here. And if we look at the zeros here, we have this would be x equals negative 3, or x equals negative 4 for the zeros. That's what I'm looking at. So at x equals negative 3, we know the parabola is going to face up because our a is greater than 1. So we know it's going to have some kind of shape like this, right? I don't really know where the vertex is. It doesn't matter, but I just can tell now here what my pieces are that are positive. So right here in this section. So from anywhere from the negative 4. So I have positive values when it's between, we'll do negative infinity to negative 4, okay, for this chunk. And then, or if I have a positive here, it will be at negative 3 up to, oh, and I can include those. I should write brackets there, make brackets. Catch that. Up to infinity. So that's the values in between these. If I were to plug any of these numbers into this polynomial, I would get a positive value. And you can kind of test that out too. You could write it in set notation, which would be, I want to differentiate. This is not my answer over here. This is the zeros that I was just using to figure out. But if I was writing set notation, I would want to write it as x is less than or equal to negative 4, or x is greater than or equal to negative 3. Okay, that's how I would write that. And then let's compare that to I, because if we took these two and multiplied them together, this is where the other one kind of failed. If I multiplied these together, I actually would get, it would look similar to that under there. But in the original, my domain for this piece is x would be greater than or equal to 0. So, x plus 3. So I'd have x greater than or equal to negative 3. That's what I would have to have. And I would also have to have x plus 4 greater than or equal to 0 in order to get the positive. So I would have x is greater than or equal to negative 4. So that's an intersection that we want to write. So this one would override, if I were to graph it, you can see, if I were to graph, let's see, there's my negative 4 and negative 3, negative 2, so on and so forth, down to infinity. So this first one, x being greater than negative 4, on the right, and then the other one is, I'll be doing a different color, negative 3, everything above that. I need to take where they overlap for my answer. So the answer for this one would have to be x is greater than -3. Or you could write it in interval notation. Okay, or it could be greater than or equal to. I'll put my bracket. So since this has a different domain than above, we wouldn't say they're equivalent. So we would say no. Okay, not equivalent. The last one here is j of x equals square root of 3x minus 5, all divided by x plus 4. So we do need to look at both situations. We can't have a 0 in the denominator. We also need to have this inside, this 3x minus 5, the radicand, has to also be greater than or equal to 0. Okay, so let's take those in two separate pieces real quick, and then we'll be done. So we have, we can't have x equal to -4. And again, we have an and situation going on here, an intersection. And we can set the 3x minus 5 greater than or equal to 0. I'd have 3x greater than or equal to 5. Divide both sides by 3, and I get x greater than or equal to 5/3. So those are my two situations that I have to have ring true. So again, just graphing it really helps. It helps you lay it out. So we would have -4, let's say like zeros here somewhere, 5/3. Okay, so I'm okay with having it greater than or equal to 5/3 going that way. I cannot have it equal to -4. I could, you know, for this piece, I could have anything else, but so I'll put that in a different color actually, so you can see it real clearly, that would be an open circle, and I could kind of go either way, right? Any other number for this piece, but I also have to have greater than 5/3. So since I really only want the overlap, doesn't even matter that x doesn't equal -4. I don't need to write that. It's all covered here. If I write this in interval notation, I would have 5/3 to infinity, or x is greater than or equal to 5/3. Okay, so those would be your two ways to write that. So I hope that helps. You'll get some domain problems mixed in with homework. It might come a little later on, so just you might want to check back and reference your notes. So that's it for this video. I'm going to do part 2 for the piecewise, probably mix range in there somewhere as well. Range is really just what your y values can be. So we'll look at a couple of things. It's really easier when we start talking about graphs to do that.